Of all of the forces at work in nature, gravity is at the same time the simplest and most enigmatic of all. It is simple because it is easily created and, at least on the scale of the everyday, easily described. All that is needed to create it is mass. If you have mass, you have gravity. It is enigmatic because we really don't know much more about it than that. We know that it takes mass to make it, but simple questions like, why does gravity only pull, and why is gravity so weak compared to the other forces, are difficult to understand. It is, at once, simple and complicated. Gravity is the force that sculpts creation, and through it, the universe takes its form. Under its influence, interstellar gas collects to form clouds that, under the inexorable crush, are ignited into stars. These stars are collected into galaxies, and galaxies are gathered into structured tendrils reaching throughout the cosmos. The effects of gravity are everywhere, and this force, more than any other in nature, is responsible for the shape of all that is. So, what is the form of the universe? How can we find out? The main characteristic that gives the universe its shape is density. The density of the universe, the amount and location of all matter, define where the gravity of the cosmos is concentrated, which bends and warps spacetime as described by Einstein's general theory of relativity. In order to uncover the geometry of the universe, we need to be able to see all of it at one time. Fortunately, we have such pictures. This is an image of the entire universe in the microwave region of the spectrum. This is what the universe looked like when it was only 380,000 years old. This is the radiant heat left over from the Big Bang. This image is full of fluctuations, tiny variations in temperature. The red parts are slightly warmer than the blue parts by only 1 part in 1,000, but they are measurable, and it is these fluctuations that give us the information we need to determine the shape of the universe. These tiny changes are related to fluctuations in the density of matter in the universe, and thus carry information about the initial conditions for the formation of cosmic structures, such as galaxies, clusters of galaxies, and voids. To understand this relationship, all we need is basic geometry of triangles. On a flat surface, all angles in a triangle add up to 180 degrees, and parallel lines remain parallel. On a positively curved surface, like a sphere, they add up to something greater than 180, and parallel lines converge. A surface with a negative curvature, such as a saddle, the three angles add up to less than 180 degrees, and parallel lines diverge. So to measure the shape of the universe, all we need is a triangle, a really big one that covers the entire universe. The all-sky map of the cosmic microwave background provide us with just such a surface within which to measure our triangle. With the Earth at one apex and 2 more points on the image, we can make our measurement. The fluctuations in the cosmic microwave background are randomly placed spots with an apparent size of about 1 degree across. They are produced by sound waves that travel through the hot ionized gas in the universe at a known speed, which happens to be the speed of light divided by the square root of 3, for a known length of time, around 380,000 years. Knowing the rate and time, we can obtain the distance to what is known as the last scattering surface, the remnants of a cosmic cloud bank. Simplifying this a little, this distance, along with the Hubble constant and the actual light path taken by the CMB to our eyes, will tell us the geometry of the universe. If the universe is flat, our triangle would have straight lines, and all angles would equal 180 degrees, and the average angular distance between the CMB fluctuations would be 1 degree. If the universe was positively curved, our lines would bend outward, and our angles would be greater than 180 degrees, and the angular distance in the CMB would be about 1.5 degrees across. A negatively curved universe would look like this, with an average angular distance of 1/2 degree. After careful measurements of the cosmic microwave background using WMAP data, the average distance between fluctuations was found to be 1 degree with an accuracy of 15% and an error of 2%. The universe, it appears, is flat. Currently, the Planck Space Telescope is taking a higher resolution map of the cosmic microwave background, and very soon we hope to have an even more accurate answer to the question of the shape of existence.